Hello everyone, welcome to the second webinar of Control System Society in IEEE Young Professionals Turkey session. And here I am Ali HAMİDOİ, Control System Society representative in IEEE YP Turkey. And it's a great honor and delight to welcome Professor Tamer Başar, who is a living legend with his works and achievements in the theory of games, both in theory and application. Hello, Professor. Thank you for your time. Your precious time and contribution in our session. I hope you are well. And the talk is entitled as an overview of, as you see on the board, an overview of advances in dynamical games. And I will moderate this wonderful event. And please see further, if one wants to see further further information about this webinar, please visit or LinkedIn, YouTube, as well as Facebook and also Instagram websites. And now I am leaving the speech to Professor Başar. Thank you.
Well, thank you.
Thank you.
Thank you very much for the invitation. It's an honor for me to give this talk to particularly within the context of this IEEE Young Professionals event webinar series. And I'm pleased to see that you are part of the extension of the Control System Society, IEEE. I have been involved with the IEEE Control System Society as well as other societies in IEEE, but mostly with the Control System Society. I was president of the society now 20 years ago. And when I was president, I did visit several places, including Turkey, talking to all young people, and also visited universities. So this, as you have heard, the title of the talk is an overview of advances in dynamic games. And what I intend to do is to give you an overview of a highlight of some of the fundamentals of game theory as well as dynamic game theory. It's going to be a high-level talk, but then I will also discuss some specifics. And as you will see now on my outline slide, I'll first provide a quick overview of basic game theory. I'll talk a little bit about the history. It has about more than 75 years of history, and still a very active research area. It has a rich landscape. I'll talk about two very important notions of solution in games, and these are known as equilibria because there is more than one person making a decision. It's the interaction between multiple individuals that really governs the dynamics of a game and the outcome of a game. So I'll talk about Nash equilibria, both for pure strategies, which means deterministic strategies, as well as mixed strategies, which is probabilistic actions by the players. I'll give you a few general results on existence and uniqueness of Nash equilibria, and then we'll talk about Stackelberg equilibria, which is Nash equilibria is a symmetric sort of a solution concept. Stackelberg equilibria or Stackelberg equilibrium is a hierarchical solution concept. You have leaders and then you have followers. And the leaders decide on some actions or strategies, and then they take the possible responses of the followers into consideration before they decide on what to do. And then the next major bullet is dynamic information and what makes games exciting, and particularly during the last several decades, is the exchange of information among the players and how that affects the equilibria. And so I'll provide some general formulations of deterministic and stochastic differential games. And those of you who know optimal control theory and both deterministic and stochastic, and this is a generalization of optimal control theory. And information structures play an important role in this more general setting. What that means is how much players know about each other and also about the environment. And as actions of the other players, as well as the environment itself, changes over time. And there are many complexities, many unanswered questions, and I'll talk about some explicit results, problems that we can solve, and then, but that leaves several unresolved issues, and some of them could be addressed within the context of mean field games, and that is a more recent development, quite a recent development, essentially in this millennia. And I'm going to be more specific in that case in mean field games, where you essentially have a large population of players and certain simplifications arise in that case. And then I'll conclude. So games or game theory, essentially, if I have to characterize it in one sentence or in a few words, it's simply a quantification of strategic interactions between entities that we call players. So it's not what a single person makes, a decision a single person makes does not determine the payoff to that individual. So it's what others also do plays an important factor. There is, as I indicated at the beginning, there's over 75 years of scientific development, and I'll tell you how it all started. And there are many Nobel Prizes. It started in 1994 forward. Of course, there is no Nobel Prize for game theory. So most of the Nobel Prizes which relate to work done in game theory and contributions made to the field of game theory were given in economics. So these are Nobel Prizes in economics. And the very first one was in 1994. And it was given to John Harsanyi, who was at Berkeley at the time, John Nash, who was at Princeton, but he was not really affiliated with any university, and Reinhard Selten in Germany. And they were given credit for their pioneering analysis of equilibria in the theory of non-cooperative games. So essentially, Nash equilibria and its extensions. John Harsanyi is best known for Bayesian equilibrium, which is an extension of Nash equilibrium. Of course, John Nash for his work on which led to Nash equilibrium in the early 1950s. And Reinhard Selten's name is there because generally Nash equilibria are non-unique. There are multiple Nash equilibria. How you can trim that, how you can refine Nash equilibria. And Reinhard Selten in the 70s came up with schemes whereby, and I'll mention this very briefly. And so in 2000, the next one was in 2005, Robert Aumann and Thomas Schelling received, again, it was a Nobel Prize in economics, but for work done mainly in game theory, for having enhanced our understanding of conflict and cooperation. So here, cooperative game theory came into picture recognition. Robert Oman was actually visited. He's in Israel, and he visited Istanbul for a conference that I had organized 10, 12 years ago, and he was a plenary speaker there. And John Nash also visited Istanbul. There was a game theory conference which was held at Bilgi University, and that was also, or maybe 10 or 12 years ago, maybe more than that. And then the 2007 is the next Nobel Prize in Economics, which is primarily for game theoretic contributions. And this was by Leonard Hurwitz, Eric Maskin, and Roger Myerson. Roger Myerson is at the University of Chicago. At the time, he was at Northwestern University, both at Illinois. Eric Maskin at Harvard, and Leonard Hurwitz was at University of Minnesota. And this was for mechanism design theory. And mechanism design has something to do with Stackelberg equilibria. I don't have time to go into that, but that's all, again, a hardcore game theory topic. And then in 2012, Alvin Roth and Lloyd Shapley again received the Nobel Prize in Economics, rooted in game theory, for contributions. And that was for this theory of stable allocations and the practice of market design. And how can you pair people up? The one application of this was, for example, in hospitals, you have kidneys that people need and waiting for kidney transplants, and you have only a few of them. How do you match the available resource, in this case kidneys, to the patients that are in need of them? So that was one of the applications of their work. So these were directly in game theory, and there were a few others in the Nobel Prizes in economics which have strong connection to game theory, even though they were not directly in game theory. But one thing I have, before I talk about those others, let me mention the Crawford Prize. This is the counterpart of Nobel Prize in biology. And John Maynard Smith received it with Ernst, Mayer, and Williams. And the reason why I have the others in parentheses is because John Maynard Smith's work is directly related to game theory and has led to what is known as evolutionary equilibria. And he developed this notion of evolutionary biology, and that led to a game theoretic concept of evolutionary equilibria, which is different, even though it's connected to, it's quite different from Nash equilibria. So another one, which is, so this is, I said 7 other Nobel Prizes, again in economics, with some connection to game theory. One was in 2004, and that was by Finn Kitland and Edward Prescott, and that was on time consistency. And time consistency, this was in the context of single decision maker problems, but it has important applications in game theory as well. And time consistency essentially means that if you have a dynamic game and if you solve it, if you have a solution over a certain period of time, and let's say for 5 years, it covers a 5-year period. After the first year, you look at the same game and then you say, should I make any adjustment to my policy? And the solution is time consistent if you have no incentive, if you are not gaining by making any adjustments to your policy, which you have determined. Otherwise, the solution that you had obtained for that longer horizon is not going to be credible if you make adjustments and change it all the time. So you have to think about, of course, if the environment changes in a probabilistic way, that has to be taken into account in the solution process. So that's time consistency is a very important concept in game theory. And unfortunately, I don't have, in my books, I have discussed this extensively, but the origin is in single person decision making, and that was the topic for the Nobel Prize in Economics in 2004. In 2016, the contract theory, again, it has connections to game theory by Oliver Hart and Bengt Holmström. And in 2017, the behavioral economics essentially looks into the behavioral patterns of individuals, but from the point of view of economics. But then there is this led to behavioral game theory, where you take into account the behaviors of individuals. Some may act rationally, some because all along the work on game theory was based on the foundation that individuals are very rational. And so they are utility maximizers. But it is sometimes the case that the individuals are not rational. So how can you build in irrationality into the solution process? That leads to the behavioral aspect of decision making. And there's more recently a prospect theory. If you Google prospect theory, you'll find out that has its roots in behavioral economics. And finally, this year, Paul Milgrom and Robert Wilson received the Nobel Prize in Economics for their work on auction theory. And now auction theory is a part of topics covered in basic game theory courses. And definitely we can, I could have included this easily, auction theory, along with other works of Nash and Selton and so on, under direct sort of game theoretic Nobel Prize. So I have, of course, seen one of you had the picture of John Nash, and on the background, what made game theory a household name was a book that was published by Simon & Schuster in 1998, written by Sylvia Nassar. It's called A Beautiful Mind. It's the life story of John Nash Jr., and he was a prodigy, and he wrote his thesis at Princeton University on game theory, and that started essentially the non-cooperative game theory that others have followed. And his, I have to say that he wrote his thesis as part of a math PhD in mathematics, and his thesis was only 28 pages long. That's the shortest possible thesis in a math department or in any department for that matter, for something that has been that influential. And you may have seen a movie, actually, A Beautiful Mind, which won an Oscar, and several years later it was produced. So again, as I indicated earlier, Nash shared the 1994 Nobel Memorial Prize, and this is how it's called. The economic Nobel Prize in Economics is not one of the first Nobel Prizes that were introduced. It's called the Nobel Memorial Prize in Economic Sciences. And as I indicated, this is the first in game theory. So John Nash had a brilliant mind, but unfortunately, in the late 1950s, early 1960s, he developed schizophrenia. And so he was out of commission for many, many years. And then he, in 1980, early 1980s, he came back, but he did not hold any permanent positions. He was hired by Princeton as an emeritus faculty. So let me share with you a sort of a personal memory. We were keynote speakers at a conference in St. Petersburg in June 2008, and John Nash and myself and my wife and Alicia Nash. And you may have, those of you who have seen The Beautiful Mind would definitely remember the role Alicia Nash has played there, as well as John Nash. Unfortunately, in 2015, so that's 7 years after this picture was taken, they tragically died in a car accident. They were coming back from receiving the Nobel Prize in partial differential equations from Norway. And then they came to the Kennedy airport and then took a taxi. And the taxi driver, I don't know whether he was drunk or what, hit the side barriers, and then they both were flown. They probably were not, did not have their seatbelts on, and then they were thrown out of the car from both sides, and then they instantly died. Very unfortunate. So in connection to control, game theory and control, I want also to mention robustness. The economists have also been interested in the issue of robustness. And the robustness arises when you have, it's a very important concept when you do any design and then you are using a model. And how do you know that the model is accurate? Especially in economics, that is an issue. But in engineering also, when you are designing a control system, a controller, it's all based on a model that you assume, but the model may not be precise. The parameters in the model may change, and you may not have identified the structure of the model precisely. So control, in the control literature, we address this problem. And in fact, this is my book with Pierre Bernard in France in 1995. And it was first appeared in 1991 and then 95, which is H infinity optimal control and related minimax design problems, a dynamic game approach. So this was, we introduced a game theoretic approach to designing robust controllers and also robust decision systems. And where you take the unknowns as adversaries and you play a zero-sum game against the adversaries. So Lars Hansen and Tom Sargent, where Lars Hansen is at the University of Chicago and Tom Sargent was at New York University, they were very much interested in this approach, and they applied it to economic decision-making. And this is, their book is called Robustness. It's a Princeton University publication. That's what PUP stands for. And they have, in their preface, they have acknowledged that all their, that the engineering sort of approach to these problems motivated them to write this book. And now, talking about Lars Hansen and Tom Sargent, they received Nobel Prizes, again in economics, in 2 different years and for 2 different things. And Tom Sargent in 2011 and Lars Hansen in 2013. But the book has nothing. The book appeared in 2008, and that was not the reason why they received their Nobel Prizes. So let me. So this was the historical sort of an introduction, an overview, and we are now at today. And I have to tell you that game normally, when a certain topical area or a discipline is around for as long as game theory has been around, for 75 plus years, you would think that the interest in it would fade away. But it's quite the opposite. The interest in game theory has actually arisen, and it has the number of papers that are in many disciplines, and from engineering to economics to social sciences, other psychology, and even medical sciences and biology, they have exponentially grown. And right now, unfortunately, I won't be talking about it here, but there is a lot of game theoretic models in artificial intelligence and machine learning, and which involves multiple agents. This is called multi-agent learning. So game theory is very rich in models and concepts. We have zero-sum. I briefly mentioned these 2 terms, the zero-sum and non-zero-sum games. Zero-sum essentially means that it's like you are playing a chess. There are 2 players, and then either one wins or the other one wins. So it's not possible for both of them to win. So the zero-sum games are those where the gain to one player is lost to the other. So conflicting, and that's why in robust control theory, robust decision-making, a zero-sum game formulation is quite an appropriate one, because you are playing a game, the controller, the designer, is playing a game against an adversary essentially capturing everything that is unknown. And then you have non-zero-sum games where it's not necessarily the case where what one gains, the other one loses. Both sides could gain, or both sides would win. Think of it as 2 companies, for example, in a market. It is possible through their policies that they can both increase their market shares, because the consumer could be motivated to buy the product that they are producing. And now within a non-zero-sum game framework, we have both non-cooperative and cooperative games. Non-cooperative games essentially means that the individuals, the players, do not come into agreement as to how they should share the resources. And whereas in cooperative games, there is a sort of a mutual understanding between the players or among the players, if there's more than 2, that there should be some sharing. So there should be some pre-game play discussion among the players. And then the question is, what is the best, if they cooperate, what is the best they can achieve as a team together? But then the next question is, how should they share or split that gain among themselves? Another classification is with regard to complete versus incomplete information games. Complete information means that the players know exactly what their what the rules of the game are, and all the variables that are in the game. And whereas incomplete information games are those where the players do not know exactly what the game, what some of the parameters of the game are. And they don't know the behavioral sort of patterns of the other players. And we have deterministic versus stochastic games. And that is obvious from the wording here, that deterministic means that if the players take actions, the outcome is a deterministic quantity. And in stochastic games, the outcome is not a deterministic quantity. So you either take the expected value of the outcome, or you look at the probability distribution of the outcome, and so on. Another classification is according to whether the game is static or dynamic. And static means there is no information, evolution of information in the game. And whereas dynamic or differential games are those where information evolves over the game, and the people and the players observe that evolution. And then there is bargaining in games, how the players bargain. I'm not going to discuss those aspects. And then the bidding processes that's also within the context of games, and also auctions, and the latest Nobel Prize in economics went to auction theory, as I indicated. So the very beginning, I mentioned Nash's name, but there was another development before Nash. And this was John von Neumann and Oscar Morgenstern, and they are known as the fathers of game theory. And there is this theory of games and economic behavior, which is a book that they first published in 1944, and then a second edition came out in 1947. And now here I have the picture of the 60th edition, 60th anniversary edition, 60 years after the initial. So this is what started. So this was 1944, but then the John Nash in the early 1950s wrote his thesis on non-cooperative games and what's now known as Nash equilibria. Now, so this was the book by von Neumann, but then actually for some people the beginning of game theory goes back to, again, John von Neumann, but many years earlier than that, and which was an article that published in German, zur Theorie der Gesellschaftsspiele in 1928. And this was essentially the minimax theorem. So what the minimax theorem, what John von Neumann showed, is that you have two individuals. This is a zero-sum game. You have two individuals, and let's say that you have a matrix. You have elements of a matrix. One player picks a row, the other one picks a column. And one player is the minimizer, the other one is the maximizer. So the question is, how should their choices be? They independently pick row and the column. And so whenever they pick one row, the other one picks a column, then you have a unique outcome, of course, which is the corresponding entry of the matrix, a finite matrix. The question is there a solution to that? In other words, what does a solution mean? The individuals do not regret on the outcome. They don't have an afterthought. They cannot say, oh, I should have picked this other one. One can come up with easy examples that there is no equilibrium. This is known as saddle point equilibrium in such a game, in pure strategies. But if the players mix, if, for example, the minimizing player says, let's say that it's a matrix of 100 by 100, the minimizing player says, I'm going to pick with equal probability and can announce that the 20th row and the 35th row. And then the other player can also announce its policy in a probabilistic way. And then the question is, does an equilibrium exist in that case? In other words, the players do not have any regret on not choosing the right policy. So this is known as a mixed policy. And Borel, who is a very, Emile Borel, a well-known scientist, in 1920s, this was raised, this question, and there were all kinds of conjectures. Yes, in mixed strategies, such finite games have a saddle point, have an equilibrium, and whereas the Borel said, no, it's false, and didn't come up with a counterexample. But what John von Neumann showed in 1928 is that no, it's not false, but it's correct. And this is known as the minimax theorem now. And many, even continuous kernel games can be, if you discretize them using quantification techniques and so on, if you can turn them, for zero-sum games, if you can turn them into finite decision problems, by that I mean the choices by each player is a finite number. And then the minimax theorem kicks in, and you know that there exists a solution in mixed strategies, saddle point solution. And what Nash did is Nash extended that result to, again for matrix games, to multiplayer games, and not necessarily zero-sum games, but non-zero-sum games, again showing that there exists an equilibrium, in that case, a Nash equilibrium in mixed strategies. So now, to make this more concrete, what I said, let me talk about the elements of games. How do we formulate games? We have players. I'm assuming that we have a finite number of players, and each player has a decision variable associated with him. It could be an action variable. And for n players, we have that. Each one comes out of a set. This set could be a finite set, or it could be an interval, for example, interval 0, 1, or it could be a much more complicated set. It could be an infinite dimensional set. So this is, I'm talking about the static games in this case, no information evolution. And the players have cost functions. The ith v sub I is the cost to player I if that player chooses action u sub I and the other player chooses action u. The other players chooses their own actions, which I'm going to represent by u minus I. This is standard notation in game theory. Minus I means all players except the ith one. So therefore, in general, what a player receives as cost, if I were giving this to an economics crowd, then I would be using not cost functions, but utility functions, which would be maximizers. Okay, in economics, they all talk about maximization and gains to players, so you want to maximize this. But for engineers, it's more cost. But you can, the theory is, of course, quite interchangeable because from cost function to utility function, you just multiply it by a -1, and then instead of minimizing VI, now you maximize minus VI. You can give it a different name as utility function, for example. So, but the important thing is that what the cost to a player is not determined by only what that player himself does, that is u sub I, but what other players do, and maybe some of them. And the more recent work in game theory is one where not all the other players enter into VI, but only players that are in a neighborhood of the ith player enters UI. But that's a detail. So these are the cost functions. And so if V sub I did not depend on U minus I, then this would be a simple minimization problem and the players would be decoupled. But in this case, they are not decoupled because the U minus I, at least one of the other players has an impact on the outcome. And so therefore, this brings us to Nash equilibrium. Nash equilibrium essentially means that we are looking for this yellow colored U star, which is again the M tuple, U1 through UM, with the property that if you fix all players except the ith one does not have any incentive to change from UI star to some other value UI. In other words, if you minimize this quantity VI of UI U minus I star over the constraint set of the ith player, then the minimizing solution would be UI star. Even if it's not unique, at least one of the minimizers is going to be UI star. So it is possible. So the UIs generally in most applications are decoupled. In other words, I choose from my constraint set an action, and that constraint set does not depend on the actions of other players. But there are other sort of applications where we may have coupled constraints. That is the action of one. I'll give an example on the next slide. The action of one player would influence the constraint set of the other player. Especially in resource allocation problems, that would be the case. So, for example, this is the first two lines here are essentially what I had on the previous slide. But here is one problem. A very simple example. This is a capacity constraint. You can view this as an internet bandwidth, for example, is C, and different individuals want to have part of that bandwidth. So therefore, the sum of the UIs has to be less than or equal to C, because if you go over the bandwidth, then you can lose packets. And it could be some other resource allocation problem as well. And so the UIs are positive quantities, and the constraint set, there is a single constraint set here, which is the set of all UI, which are less than or equal to C. Now, what is a reasonable cost function in that case? A cost function could be, and this is actually where the utility is a better way of approaching this problem. You choose a utility function which would be increasing in U sub I. So in that case, VI would be decreasing in U sub I. The more bandwidth you use, the happier you are, the better is your preference. And so if that's the case, then what is a Nash equilibrium here? And you can see that there are multiple Nash equilibria. For example, one possibility, it all depends who takes the first initiative. The ith player could take the entire bandwidth unless there are additional constraints on that. And so therefore no additional bandwidth is left for the remaining players. So that's an equilibrium, and for any player that could be a choice. And there has to be a protocol which avoids, to make this more meaningful, which avoids exceeding the limit, so therefore the C, so that the players are penalized for that. But clearly this fits the definition, what I have at the bottom here, fits the definition of a Nash equilibrium. If you fix all other players at 0, then the ith player definitely would take the entire bandwidth. And if the ith player takes the entire bandwidth, all the other players take 0 bandwidth, then except one of them, then the one that's left, the best he can do is take the 0 bandwidth, because it will otherwise violate the constraint. Of course, one can make this more meaningful by introducing additional constraints and so on. But the whole purpose of this is to show you, first of all, that there are multiple Nash equilibria, and that you can have problems where you do have coupled constraints. So the next one, the only thing that's different on this slide is the last bullet, the saddle point equilibrium, which is I mentioned the saddle point equilibrium. It's when I was talking about von Neumann's 1928 paper. And essentially, it's a special case of Nash equilibrium. And that's why you will see papers, particularly in computer science, where they refer to, even if you have a two-player game and what one player wins, the other one loses, still it's referred to as Nash equilibrium. And this is true because saddle point equilibrium is a special case of Nash equilibrium when the cost of one player is minus the cost of the other player. So therefore the V1 plus V2 is equal to 0. That's where the zero sum comes from. And then M equals to 2. That is, there are only two players. In that case, you can easily write the Nash equilibrium in this way. And this is what I have in the middle is essentially the V, which is the cost to the first player, which is utility to the second player. And so V is what the first player wants to minimize. So this is the right-hand side inequality essentially says that if U2 is fixed at U2 star, then U1 star minimizes V. And likewise, the left side inequality says that if U1 is fixed at U1 star, then U2 star maximizes V. Okay, so that's the saddle point equilibrium. Those were static games with deterministic framework, where if players pick actions, then you know exactly what the outcome is going to be. Now, that's not always the case. You have some random state of nature, and let me denote it by X here. And generally, players make observations on X, and that may not be an accurate observation on X, but it may be a noisy observation, just like in communication or in control problems. So the player I will make a measurement Z sub I related to X, correlated with X, but it doesn't reveal the true value of X to that player. And the assumption is that you know the joint distribution of X Z1 through Zn. All players have access to that. So that's what I meant by complete information game. Complete information does not mean that all players observe the same thing, but all players know the underlying statistics of the game. So the joint distribution is known. And so when you have a measurement like this, the action is determined by a mapping from the measurement to the action space. And so for player I, you have gamma sub I. So this is now a new entry into the formulation. This is known as a strategy or a policy, which is very important in game theory. And so gamma I is a mapping from the space where the ith player's measurement belongs to that player's action. And you can make all kinds of assumptions. Generally, the most general would be measurability. Gamma I is a measurable mapping, and you can have other very special mappings. You can say, I'm only interested in linear mappings, for example. Whatever the problem and the specific application dictates, we have a capital gamma I here I have, which is known as the strategy space. So gamma I belongs to that. So now the players, instead of picking actions, they pick strategies, or sometimes known as policies. And so once a player picks a policy gamma I, then, and the player can do this before he observes what the measurement is. So once the gamma I is picked, and then the measurement comes in, you apply gamma I on the measurement, and that tells you what action you should take. So now there is, you don't have a single cost function, but for each player, but you have a loss function and a cost function. The loss function depends on this random state of nature. V sub I depends on the random state of nature, as well as on the control of agent I, or player I, or the action. Let me say action here, control I'll introduce later, and also the actions of all the other agents. So this is like the VI I had earlier, but I have an additional X, which is the state of nature, which makes VI a random quantity, even if UI and U minus I are deterministic quantities. So therefore you take the next step, you say UI is going to be generated by gamma sub I, by the policy. So you substitute that in for, as I have at the bottom here, Uj for the jth player is gamma j of Zj. So you substitute that in here. And then now this is a random quantity because it depends, of course, on the gammas, but also it depends on the actual realizations of X, Z1 through Zj. And the players do not know this ahead of time, at the time when they are going to determine their strategies. So therefore, you have to take the expected value of V sub I, and that's what the next to last line shows. You take the expected value of V sub I over X and over also the statistics of Z1 through Zm. And with gamma j given. And so that this way you average out the X, Z1 through Zm, and you end up with gamma I, gamma minus I in the cost function. And this is known as the normal form of the game. Now you introduce a Nash equilibrium with respect to these strategies and not with respect to the actions. So that's the real game theoretic formulation, in fact, because this encompasses and assumes as a special case the situation when gamma sub I is a constant. That is, there is no measurement. So you just pick a U sub I. So that's captured by picking gamma sub I as a constant map into UI. So you ignore the Z sub I. Okay, so this encompasses the earlier one that I had. So the Nash equilibrium is the same, and now you define it in terms of the gammas. Okay, so let me just mention very briefly a different equilibrium concept. This is the Stackelberg equilibrium. So what you have in that case, in the Nash equilibrium, the roles of the players are symmetric. You have all of them, all M players, they don't have any hierarchy in decision making, and there is no priority in their decision making process. But that's not always the case. For example, a government has a taxation policy, and the citizens have to abide by that. So therefore, the government is the leader, and the citizens are followers in that case. So you have, and this could happen in also companies. Some companies may be more dominating, and then they may decide on the price, and some other smaller companies will have to follow that. So you have one leader, and in this case, you can have multiple leaders, but let me discuss the one leader case. You have one leader and M followers. So you have a total of M plus 1 players in this case. Let's say that player 0 is the leader. and has a cost function, again, given in this way. So I have introduced an additional one u sub 0 here. And then the player I, that is the follower, is a cost function, again, of the same type, vi. These are all different cost functions. Of course, different players will have different cost functions, u0 through un. Now, what's a Stackelberg solution? The leader will have to come up with an action. So this can be extended to the stochastic case as well. I don't think I'll be doing that here, but let me just talk about the static deterministic case. The leader will have to decide on a u0. Now, it knows that the followers are going to respond to that, and the responses of the followers are going to affect the performance of the leader. So therefore, what the leader will do is, before deciding on u0, will have to anticipate what the response of the followers will be. And let's say that the anticipation is, this gives you an L of u0 star. This will be the response under some solution concept, and among the followers, you can assume a Nash equilibrium. Let's assume that L of u0 star, so to each u0, you have an L of u0 as the response of the followers themselves. If there's only one follower, this is the response of that single follower. So what the leader will have to do is take that as a given, L of u0, and note that this is again a complete information game in the sense that the leader can compute L of u0 because it knows the cost functions of all the followers. So then you minimize this with respect to u0 and then obtain a u0 star. Okay, so that will be the Stackelberg solution for the leader, and whatever the L of u0 star is will be the corresponding solution of the followers. Okay. So this is an optimization problem for the leader, subject to some Nash equilibrium constraint, because the followers are going to do a Nash will obtain a Nash equilibrium solution. This has to be, in this formulation, I assume that the Nash equilibrium solution by the followers is unique. It's a pure strategy Nash equilibrium. That's what PS stands for. If it's not unique, then one has to bring in other constraints. And one comment here is that the Stackelberg equilibrium, we can view it also as a Nash equilibrium of a new n+1 player dynamic game, where the UI is now UI of 0. In other words, the followers have access to the action of the player. So this is no longer static. And so therefore the followers will have dynamic information, but the leader still has static information. So that's another interpretation. The solution does not change. If L is not unique, then one looks at whether you are pessimistic or optimistic. The leader, generally one approach which is consistent with the robustness issue is that you say that I'm going to prepare myself for the worst possible outcome as far as the follower's choice goes, and then pick a u0 star accordingly. Okay. So now this was all with pure strategies. We can extend notions and definitions of Nash equilibria and Stackelberg equilibria to mixed strategies. Equilibria. So mixed strategy is simply a probability distribution on the set of actions of a player. I just introduced you to mixed strategies when I discussed the minimax theorem earlier. And so you can view in that case, a mixed strategy as a random variable. And these random variables are independent among players. And now there is another, and this was introduced by Ullman, whom I mentioned earlier. these random, generally, when you look for mixed strategy equilibrium, the random variables are independent. In other words, pick individuals. If you have two players, say in the matrix game, and you have to toss a coin or roll a die or roll two dice in order to decide on what to pick. So that's a random mechanism. The other player will do the same thing independently. And because the outside, if two players toss coins, let's say that they have to pick between two possible actions, each one, then this is an independent experiment. And but there are sometimes applications and scenarios where these two choices could be dependent. Quantum computing, in quantum computing you have that, but that's not the topic I'll be discussing here. There's a lot of interest now recently in quantum computing and use of game theory there. But the example that the Orman had introduced is, for example, if you have a traffic light, so this is an outside signal, and the players will abide by the traffic light, and whether they will decide to cross the street or not will depend on the outcome of that signal. So therefore, their strategies will be correlated in that case. So, the Nash, I indicated earlier that Nash extended the minimax theorem to to non-zero sum games, to Nash equilibria. And I'll not go into details of this, but essentially the important thing is that U sub I will have to be a finite set. So you have a matrix game, only a finite number of actions by the players. And then there's a cost function for each player. You have a probability vector on U sub I for each player. You decide on, since it's not difficult to characterize that, this is essentially, you attach to each element of UI a number between 0 and 1, and they have to add up to 1. That's a probability vector. That's what mu sub I is. So if players picks mu sub i's, then you have the expected value of VI, and then which is I denote here by J sub I, and then you have the Nash equilibrium in the standard sense in terms of the mu's. And what Nash has shown in this paper in his thesis, 1950-1951, a paper published in the Annals of Math, and used Kakutane's fixed point theorem to show that there actually exists a Nash equilibrium in mixed strategies. Okay. Now, how does one extend this to continuous kernel games? And this came later in the 1960s. Continuous kernel games are those where these are known as infinite games. You have compact action spaces. For example, each player will have to pick a number from the interval 0, 1, let's say, as an example. And or you have a sphere, and the players will have to pick a point on the sphere. So there's an infinite number of possibilities in that case, but you have the compactness. And then if their cost functions are continuous also on these action spaces, then one can show that there exists a Nash equilibrium in mixed strategies. These are probability mass functions on U sub I. And if further the V sub I is convex, so you can bring in some topology into the problem because you are in infinite spaces, then there exists a Nash equilibrium in pure strategies. And if you further have differentiability, the way, along with convexity, the way you obtain this Nash equilibria is you take the derivative of VI with respect to the ith player's action, and then solve. You obtain M equations. You solve these M equations, and we know that a solution exists in this case if you have this condition, and VI has some growth properties. This happens if the UIs are open, but and openness, of course, conflicts with compactness. So that's why you have to have some growth conditions. One thing is that if you have, the question is what happens if you have multiple Nash equilibria, and how do players, I mean, this is a non-cooperative game. This is one of the downsides of Nash equilibria, unless you have uniqueness. And so let's say that the game has two sets of Nash equilibria, and the one player picks one, and the other one player picks another one, which doesn't correspond to the one that the first player had picked. Then these are not going to be in Nash equilibrium. So that's what this means. Multiple Nash equilibria are not necessarily interchangeable. But if you have the special case of zero-sum games, then you have saddle point equilibria, multiple saddle point equilibria are interchangeable. So there's no problem there created by non-uniqueness. The opposing players can pick any choice from the solution set corresponding to them. And this issue with multiple Nash equilibria really created a lot of concern in the community. And that was one of the things that Reinhard Selten did. And also I did around the same time. You bring in some refinements to remove non-uniqueness. And one of these refinements is to say that if a player has to pick one action, this is known as a trembling hand equilibrium, since there is it comes from in this case, it was a finite game, you accidentally, with some low probability, pick some other action. So you take that into account, and this way you can eliminate some of the multiple Nash equilibria. This is known as a trembling hand equilibrium. So that brings in some sort of a robustness into the selection process. Okay, so the dynamic games, now you can introduce dynamic games in two different frameworks. One is using difference equations in discrete time. The other one is in continuous time. Here I choose to do it in continuous time because I knew I'm already at the 1 hour mark. So it is the discrete time counterpart can be found in my book, with also which I'll reference later. So, and this is for those of you who know optimal control in continuous time. This is also very much connected to that. It's you can view this as a generalization. So this is stochastic. I will bring in stochasticity a bit later, but at this point, this is deterministic. So you have the derivative dx, you can bring dt here. Dx dt is equal to f of x ut, and the u is again the controls of the players. In this case, these are controls. And then this is eta is what information a player has access to. And I have listed here a number of possibilities. We have the open loop case where all the players only know the initial state x0 and cannot observe the state during the evolution of the game. There is a closed loop with memory, which means that they observe the evolution of the state from the beginning, 0, up to t. So this is a causal policy. And this is the information that they use. You have closed loop no memory, which means that they know where this game started, x0, but they haven't observed up to, or they may have observed, but they forget about it. There is memory restriction. They only remember the state at the present. So they know xt and x0. And then there is closed loop with delay, d, which means that they simply, for the first d seconds, they just know the initial state. From that point on, they observe the state with a delay of d time units. So the cost functions for the players is L sub I is the cost function or loss function, which is an integral in all these problems. It's different for different players, G sub I. And so depending on the information structure, so this is very important in dynamic games and differential games, then you have a different type of a policy or strategy. Gamma sub I, gamma super I, here I have superscript for the players, is a function of eta I. So that's on the second line, that's what I have. Gamma, at time t, the policy for the player I is a function of the information available to that player, okay? So this started, the differential games started with the work of Rufus Isaacs, who was at Rand Corporation in the early 1950s. And he published, this was in the zero-sum game framework, not non-zero sum. This is known now as pursuit evasion games. And for a long time, his work was classified because it was related to war games. And the Rand Corporation was mostly was working on military projects. And this was also about the time those of you in control know about dynamic programming. What Isaacs developed for games, for zero-sum games, parallels what Bellman developed for dynamic programming for single person optimization, dynamic optimization problems or decision-making problems, which is known as the principle of optimality. And Rufus Isaacs essentially developed the counterpart of the principle of optimality for pursuit evasion games. But because since it was all classified, it was not known until he published a book in 1965. Okay, by that time, the Bellman had already published his book on dynamic programming, and it was well recognized. So the stochastic differential games is one where you have the state equation now is a stochastic equation. So there's this additional term that I have where W is this is like in stochastic control. Think of this as in stochastic control where you have a white noise driving the state equation. So W is known as a Brownian motion. And the dW, so this is the so-called the Ito representation way of writing it, where you have the change in X is F times the change in time dt plus some sigma, which is a weighting here, times the change in W, Brownian motion. Okay, in other books you can see this as written as dxt dt equals to F plus sigma times dwt dt, where dwt dt is the white noise process. Now, there's also a measurement process in stochastic differential games. Each player, just like I had earlier in static games, each player has a measurement, Z sub I. And that also, think of this as a channel, a measurement channel or a communication channel, which is noisy because the VI is the noise, which provides information on X to that player, on the state of the game to that player. And now the players policies will be functions of Z as I had in the stochastic games, and not as a function of X because they don't have access to X. So the eta I in this case is essentially depends on how much of the Z a player remembers, and that's what's functional. So the loss function is the same. You take, once you decide on the gammas, then you substitute it in place of the UIs, UI, U minus I. You take expectation over the statistics of W, these are the random quantities, as well as X0, the initial state. And then that leads to, again, once you substitute all this in, you have a sort of in abstract form, a similar type of a J, so, which is a function of the policy strategies. And you can introduce a Nash equilibrium in that case, but it again depends on the information structure that one has. Okay, so you can introduce, define Nash equilibrium in this normal form. This is known as the normal form of the game. So it doesn't really, as far as the conceptual notion of equilibria goes, it doesn't make any difference whether you have a stochastic differential game or a static deterministic game. It is all you have to bring it to a normal form and define the Nash equilibrium that way. Of course, to compute the Nash equilibrium, you have to go back then to what we call it extensive form of the game. Okay, so here are different sort of possible information structures for the game. Again, it involves ZTIs. Open loop is no information. Local information with memory. So each player has a measurement channel, looks at the output of that channel, and that's ZI over the interval 0 t, remembers what happened in the past. You can have local information with absolutely no memory. You forget about the past and only use, you are allowed to use what you observe now for your action now. And this is again the local information. By local, I mean local to that player. Now you can have total sharing of information with memory. In other words, which means that the other players also share what they have observed. They have independent channels, but they all share the outcome or the output of those channels. So this is known as total sharing. You can have total sharing with delay, and you can also share. You can have a network topology in the game where you introduce neighborhoods, and the players can only share information with their neighbors. And that's, again, another information structure. So the Nash equilibrium, so those are the details as far as the definition of a Nash equilibrium goes. So this is, again, the Nash equilibrium. And the solution approach is if you have compatibility with the information structure, you can temporarily decompose, like in dynamic programming, into single stage games or time frozen games for each time, and which are essentially static games, just like dynamic programming does, and then obtain the Nash equilibrium of each game. But this is only if the information structure allows for such a decomposition. I won't be able to go into the details of this. Or you can use the maximum principle if it is an open loop information structure. So in optimal control, you have dynamic programming and maximum principle. Dynamic programming is used if the controller has access to the state. It gives you a feedback policy, optimal policy. Whereas in the, if you have, in optimal control, if you don't have access to the state, but only know what the initial state is, then you use the maximum principle, or known as the Pontryagins maximum principle. But if the players generally, in all reasonable applications, you have asymmetric information by the players. They either don't share their information with each other, what they retrieve from the environment and through their measurement channels. And then in that case, the Nash equilibrium is extremely difficult to compute because such a decomposition is not possible. And one of the reasons for this, when you have asymmetric information, is the strategic interaction among the players. The players will have to guess what other players have observed, because that information, if they guess it right, that information could be useful for those, for them to improve their performance. But what if all players are doing this? This is known as a second guessing phenomenon, which involves an infinite recursion. Even if we have two players, I try to guess what the other player has observed from how it affects my dynamics. And then the other player will have to guess what I have observed through the impact of my control on his dynamics. But then I have to guess what the other player has guessed about me, and so on. So that's an infinite recursion. And that makes games with dynamic information structures, if it is not a decomposable one, very difficult to solve and even impossible to solve. So let me just share with you this picture which I put together. This is for static problems. This is where non-zero sum games sit in a decision-making phenomenon, and where zero-sum games sit. Zero-sum games is a special, this is all for static games, is a special case of non-zero-sum games, as I indicated, with only two players, and what one gains, the other one loses. And then you have teams, another special case. What I mean by teams is that all players have exactly the same cost function, even though they may have different measurements if it's a stochastic game. Okay, so the teams, this would be a special case of non-zero sum games, because you are, you essentially have all the loss functions or the cost functions of the players are identical. So they are all essentially minimizing the same cost. Now, the solution concept for non-zero sum games is Nash equilibrium. There's also stackable equilibrium, but let's talk about Nash equilibrium here. For zero sum games, the special case of Nash equilibrium is saddle point equilibrium. And for team problems, the special case of this is the so-called person-by-person optimality. Now, when you have teams, you have a stronger notion of a solution, which is global optimality. And every globally optimal solution is also person-by-person optimal solution, but not every person-by-person optimal solution is a global. So there is another step there. But if I want to embed this in this diagram, I have to put down person-by-person optimality, because that's the one that directly corresponds to Nash equilibrium. Now, if you have dynamic scenarios, then instead of team problem, we have optimal control problem. And then you have the non-zero sum dynamic games or differential games, and then you have zero sum dynamic games or differential games, okay? So optimal control is a special case of non-zero sum dynamic games. And now let's see, it's almost an hour and a half, and let me, maybe I'll skip some of these slides and then discuss with you some mean field game results. So here on these slides, I had a few cases where we can obtain the solution explicitly. for all players, Nash equilibrium with closed loop perfect state information. Essentially, it involves solving coupled partial differential equations in the most general case for stochastic games. And for linear quadratic games, those of you in control who have dealt with linear quadratic regulator problem or LQG problem know that the Riccati equation arises quite prominently. And in this case also you have Riccati equations, but so you have a quadratic cost function here in terms of all the controls of all the players, and then you have a linear system, and you have coupled Riccati equations. So if these coupled Riccati equations admit a unique solution, then you have a unique feedback Nash equilibrium, which is linear in the state, x sub t. But note that this is not linear in the local state. If I want the solution to depend only on the local state, then I cannot do it using this approach. So this is the thing: when information is local state or imperfect state measurement, even if it's shared by all players, existence and characterization are open problems, okay? And so this brings me, so the question, because of this difficulty, even in the linear quadratic case, it is with local information, it's almost impossible to obtain the Nash equilibria. So the researchers have, including us, we have looked into other possibilities to overcome that difficulty. And one possibility is to look at the case where, in order to remove this strategic interaction among the players and to remove the second guessing phenomenon, to go to a high population regime. That is, assume that there is a large number of players. How can we obtain the Nash equilibrium in that case? And that leads to the mean field games framework. So let me bring you back to the book, which I said is what started the field, the one by von Neumann and Morgenstern. The first edition of the Theory of Games and Economic Behavior, 1944. On pages 13 to 14, they say, when the number of participants becomes really great, some hope emerges that the influence of every particular participant will become negligible and that the above difficulties may recede. By difficulties, it's not quite the kinds of difficulties that I was alluding to here, but these are, they realize that if you have the strategic interactions among players, not in the context of dynamic games, but other more specialized games, would disappear maybe. And but they don't do anything more on that in the book. And but this is a very sort of an insightful comment. It's well-known phenomenon in many branches of the exact and physical sciences that very great numbers are often easier to handle than those of medium size. This is, of course, due to the excellent possibility of applying the laws of statistics and probabilities in the first case. For example, in thermodynamics, you don't look at if you have atoms in a chamber, you don't look at the dynamics of each atom, but you look at the probabilistic sort of movements of the atoms. And even though each atoms, you can view them as players colliding with each other. So the mean field games is essentially makes use of this large population property and the fact that, or the possibility that, because it still has to be proven in different contexts, that the individual players do not have much influence on the outcome of the game. and it's the population of the players that make a difference. So you have a large number of players or agents. They are coupled through dynamics or cost functions, and it has to be a special structure, and I'll show you the special structure shortly. It's through an aggregate quantities. For example, the average of states of all other agents, or fused information received from other agents. Each agent will interact not with an identifiable agent, but with a population of agents and response to the population. One example that one can give, if you want to go to the beach and then you see lots of crowd there, and you want to pick a spot there for sunbathing and on the sand. And so what you do is you don't look at individual people there, and you simply look at the crowd where if there's a high concentration of crowd, you try to avoid that, you go to a low concentration part. What if every player does that? Note that the players are not responding in that case. Individuals are not responding to individual players, but they are responding to a population. And so that's the idea behind these mean field games. And so through this approach, we can actually solve a large class of stochastic dynamic games. And this is still a very active research area. And we can solve games which otherwise would be intractable if we take the direct route. Okay, so here is a mean field formulation. So it has to be a special formulation. So this is the state equation I had earlier, stochastic differential equation, but this is the equation for the ith player, dynamics of the ith player. And note that it depends, of course, on the state of the ith player and the control of the ith player. But then it depends what I have here in red, what we can call an aggregate quantity or an average quantity. So it depends on the states of other players, but the states of other players enter through an average term. So it is the average of the states of the other players. So the players, this is known as the mean field term, especially if M is large. And so the players are coupled through the mean field term. In the loss functions, you can have the same thing. And again, the loss function of the ith player depends on the state of the ith player, control of the ith player. If I did not have this red term here, and I didn't have the red term here, these would be independent, decoupled control problems, optimal control problems. It wouldn't be a game. What makes this a game is the coupling through these terms. But the coupling is in a special way, and that special way, this is through the average, okay? So the approach to mean field, I will not go into the details of the derivation, but just give you a summary of how the problem is approached. Now, you say when M is sufficiently large, now normally if you want to solve this problem for the ith player, you have to take into account the impact of the ith player on this term. But if there is a very large number of players, then you can take it as an exogenous process, as a stochastic process, fixed stochastic process, but we don't know what the distribution of it is as yet. And let's call it Z sub M, okay? And the assumption here is that this is not affected by the PI's choice of control input. And because the X sub J would be affected in general by if I have a very few players, by the ith player's state, which is in turn affected by the ith player's control. And so therefore the XM would be affected by ith player's control. and that has to be taken into account in the optimization problem. But if M is sufficiently large, we can take Zm to be an exogenous process. So then what that does is it decouples the players' optimization problems. You solve the stochastic control problem faced by each player for each fixed Zm. And this is known as a Makin-Vlasov equation because you have a distribution here. And then, so after you solve each player, you substitute them back here, and then you generate the state process under these optimal controls, and then you require consistency. You have a state process, you take the average of that state process, but that average has to equal to Zm that it's a function of. And so that involves a fixed point equation that one has to solve. So there's a lot of mathematics behind this, but for some classes of problems, we can obtain the solution explicitly. And then what we have to do is let's say that we're not really interested in an infinite population, but a finite but large population. Then the question is the solution that we obtain for the infinite population, to what extent it provides an approximate solution, Nash equilibrium, for the finite population game, and that can be investigated. So here is the one specific case, just so that you can develop some intuition into what that term plays. This is known as a consensus problem, a linear quadratic formulation. Consensus problems have applications in social sciences and has applications in flocking problems, for example, when different aircraft want to follow each other. And so many tracking problems which involves multiple agents, multiple controllers, can be formulated as consensus problems. So here, this is a special case where the state dynamics of the ith player just depends on the action of the ith player. So the other player's states do not enter into X sub I. The only place where the coupling shows up is in the loss functions of the players. And note that what that means is that essentially the player I wants his state to be as close as possible to the average states of all the other players. So he wants to minimize the difference between this, and this is a norm squared. And then while doing this, wants to use minimum effort. So trade-off between the two. But this is this is known as a consensus problem because you want xi to be close to the average to the extent possible. Okay, so again, to solve this problem, you treat xm as a fixed stochastic process, not affected by PI's choice of control input. Now, by the strong law of large numbers from probability, Zm in this case, since because of linearity and so on, becomes a deterministic process. So the Zm here, or the Xm, is a deterministic trajectory, which the ith player, as well as other players, it's the same trajectory for all players because it's an average, and all other players want to track. So you solve the stochastic control problem faced by the ith player for each fixed Zm. So this is a tracking problem, and the solution in that case is affine. Not linear, but affine. There's a linear part and a part which depends on this exogenous process, which is deterministic. You generate the state process under these optimal controls, require consistency as m goes to infinity, which again, as I had on the previous transparency, entails a fixed point equation. And then you study the relationship between finite m and infinite m solutions. And then the kind of approximation the mean field equilibrium provides for the Nash equilibrium for the finite population game. I'll just give you the results. So this is the problem, and we look at the problem as t goes to infinity, that is for the infinite horizon, so that we can have steady state. And here's the solution. I said we have an affine solution, so there is a Riccati equation that P satisfies. And so you have the linear term, feedback term, and plus a term which depends on Z. So S is the integral of Z. And then you substitute this into your system, for U. And this is the same for all players. This is for a generic player. And the generic player's resulting cost function is this now. And then you now have to, so I reproduce everything here. You have to solve the fixed point equation, and the fixed point equation is, again, by the strong law of large numbers, the expected value of x theta over the statistics of theta, x, and w theta should be equal to z of tau. And this is, theta is the type of the player, and we are assuming that here that the players could be of different types. But we can show there exists a unique fixed point using a contraction argument. And then the last part is, how does it connect to the finite population game? I know that this is fast, but just to give you an idea, we can show that it's an epsilon Nash equilibrium. Epsilon, how small or how large epsilon is depends on M. But if you have uniform agents, then the epsilon is in the order of 1 over square root of M. So that's how it goes. So if M is 100, then it is 0.1, like that. This is the approximation error for the Nash equilibrium. If it is 10,000, then it's 0.01. Okay, so let me conclude by saying that dynamic game theory offers really an exciting landscape for future research for many years to come. And there's a rich portfolio of problems. And right now we see in multiple communities the convergence of game theory with artificial intelligence, machine learning, and learning in a general sense. I mean, all what I presented here is essentially the rudiments, was the rudiments of foundations of game theory, with the exception of the last part, which is much more recent work. But there is a lot more recent work which deals with problems of learning. What if the players, you don't know the actual model of the system, of the game, the state dynamics and the cost functions? Can you learn it online? So there reinforcement learning comes into play. And this is my last bullet, which says that the game theory along with reinforcement learning provides a fertile direction for robust controller designs as well, and data-driven. So that's the other important thing. As you want to do these things not offline, but online, as you learn more about the system you are controlling. And this is known as model-free, data-driven controller design, robust controller design, or policy design, for that matter. So let me, I have a few references here. The basic reference for the first part, the foundational part is on my book on dynamic non-cooperative game theory, which first appeared in 1982 in Academic Press, and then the latest version by SIAM in 1999. We published the Handbook of Dynamic Game Theory. Everything that I talked about, the auctions and cooperative games and dynamic games, differential games, if you want to learn about that. It's a Springer Verlag 2018. George Zakur and myself are editors of this. It's a 2-volume work. The robustness, so this is the one I mentioned, Lars Hansen and Tom Sargent, 2 Nobel laureates who were motivated by work in robust control, the game theoretic approach, and which they then used it in their in economic decision making. And so this is that book. The second version, 1995, is more complete. H-infinity optimal control and related minimax design problems. There is a lot of application of game theory in network security. And so we have a book with my, an earlier PhD student of mine, Tansu Alpcan. He did his bachelor's at Boğaziçi University. And this is Cambridge University Press. He is now a professor at, in Australia at the University of Melbourne. And this is when I was, before the, I started the presentation, a question was asked on applications to communication networks of game theory. So this is a recent book, again, Cambridge University Press by Han Niato, Saad, and myself. And so these are the main, of course, these are biased toward my presentation here and some of my work. There's a very rich literature by others as well, but by looking at these 5 sort of books or encyclopedia or handbook, you can get a fairly good, complete idea on the vast opportunities that lie in game theoretic research. So I talked about mean field games as the last part. The serious work on mean field games started with 2 pieces of work. Lasry and Lyons from France in 2007, and Juan Keynes and Malhame, again 2000. So these were independent parallel works, and they were emphasizing different aspects of mean field games. The Lasry and Lyons paper was mostly on the PDEs, and this is, the second one is more control oriented. And I didn't discuss risk sensitivity, so this is one way of bringing in robustness to these problems. The first paper on risk sensitive mean field games is with a former student of mine, or he was a student at the time, Kwang-Yan Su, now a professor at New York University, and HAMİDOŞ also at New York University. And so that's 2014. And several other papers, again, my former PhD student, Jun Moon, who is a faculty member in Korea now, we published quite a number of papers on robustness issues in mean field games with risk-sensitive control. And then we had also applications in social networks through mean field games, and again the work with Jun Moon, and this one, the fourth one, is also with Jun Moon on risk-sensitive mean field games. And then the very general sort of a Markov decision-making problem-oriented work in mean field games are in these 3 papers. With Naci Saldi is with Özyeğin University. He was a postdoc at Illinois, and we did this work when he was a postdoc. He's now a faculty member. So those of you who want to know more about mean field games, I mean, he's local there in Turkey, of course, in Istanbul. and Max Waginski is a colleague of mine at Illinois. So we published a number of papers on a very general approach to mean field games in discrete time with discounted costs. It appeared in Science Journal Control and Mathematics of Operations Research. So this diversity shows you that different communities are interested in these problems, both control and operations research community, and of course the game community itself. So that's where I will. Oh, let me just the last slide. I entered these as listed these as an indication of my last bullet on the conclusions slide, that the learning, some of the recent work on games which involve learning and which brings in artificial intelligence, machine learning to the table, is some representative papers are these. They are my current PhD students or postdocs. And so we published a number of papers on reinforcement learning in applied to mean field games. And again, the multiple communities, neural information processing systems is a computer science mostly conference and a very selective one, but they're all interested in these problems. So I'm going to stop here. So it took much longer than I thought it would, but I hope it gave you a good overview of research in game theory, both the old and the new. If you have any questions, let me know. And I should also mention that if you have any questions after, because of time limitations now, you may not be able to raise all the questions. You can write to me and send an email, and then I'll try to respond to your questions. Okay, thank you.
Thank you, Professor, for your wonderful talk. And actually, we have several questions about this presentation. Let me start my own questions. So actually, I would like to mention about a problem that Rufus Isaac proposed in his book. Actually, this problem is about two-player games, pursuit evasion games. One player is called pursuer. You know, he tried to catch the invader, which is the second player, and as close as as far as its origin, and the goal of the invader is to be catched near the starting point. So this is somehow like as you explained in your talk. This is about saddle point equilibrium problem, right? So we can design that equilibrium for that dynamical game. Actually, there are lots of such problems in two-player matrix games. For example, one like location of attackers and location of protectors that protecting some region. There are some problems like that. My problem is
protecting there are problems where you are protecting the harbor, for example.
Yeah, exactly. The basement. Yeah, exactly. I'm a little bit interested in these problems. So here the problem is actually we have a dynamical process actually. So one pursuer following and invader also. So is it possible to discretize that model, that continuous model, dynamical model, and then possess a discrete pursuit invasion games? Is it possible for this? For example, we can use either discretization technique. Actually, there are many techniques for that. So is it possible to design, for example, a discrete two-player pursuit invasion games? And the problem is, for example, the pursuer is catch the invader only if it traps its opponent within an epsilon neighborhood.
Yes, well, I mean, you have to construct a matrix game, entries of a matrix, corresponding to that, which captures, of course, you cannot be, it's like you have a mesh, for example, in any pursuit evasion game, you have a mesh, and you want, it will have, let's say that it's on the plane, a two-dimensional plane, and then you have different sort of cells on that plane, which are squares, and so the players, you say the game ends if the two players are closer than a certain three cells. And so that you can capture as a matrix game, as entries of a matrix, and of course, as I indicate, it's a zero-sum game. Which will always have a solution, but the solution is not going to be in pure strategies. Generally, matrix games have, von Neumann's result says that there exists a saddle point in mixed strategies. Now, that doesn't mean that there isn't a saddle point in pure strategies, but generally these pursuit evasion games will involve mixed strategy solutions. Because if it is a pure strategy solution, then the players will know exactly where each one is going to be at any point in time. So it's either you can capture with probability 1, or you cannot capture with probability, or you can capture with probability 0.
Yeah, so this is another,
and obtaining the for zero-sum games, essentially to find the minimax, to find the saddle point equilibrium, the mixed strategies is essentially an LP problem, linear program. So there are very efficient ways of solving that problem.
So actually, Professor, this becomes as it could be considered as a static game, right?
Right.
Possible, right? Because we have a finite state, and we are taking. Actually, I am. This is like an extended question. Sorry about that. So actually, could it be possible to control those locations of each player? For example, if the main aim of the pursuer is to catch the invader, so if it follows the way of the invader, so if we put some controls, I'm talking about discrete points, which could be seen as a control. So we have actually a recurrence relation actually. So each recurrence relation determines the move of each player. So actually we can, each point can be controlled by some controls, right? It can be seen, and those controls can be taken in one set, finite set, right? So
you can, I mean, in that case, if the players observe each other's location, so you can either play the game blind game, which is an open loop solution, and so you come up with a policy, a mixed strategy, regardless of what the other player does, you follow that strategy. Or you can formulate it as a dynamic problem, in which case it will be the strategy, which is a function of the location of the other player. But these strategies, you can quantize them, and even if it is in the this is what I call the normal form of the game, in terms of the strategies of the players, but you can also discretize the strategies themselves. And so therefore it becomes a much larger matrix game still.
I see. So, So, and also for new field game, I actually see it is like popular in these years. So it is like stochastic game. So we apply actually stochastic in your paper. You apply stochastic maximum principle. So we can also consider deterministic games in this field, right? So and as you mentioned
the mean field has to be deterministic in that case. And then definitely you can use deterministic.
But it becomes as you mentioned before, it becomes like a weak situation because you don't know. Actually, the deterministic case is like a strict. So it's not like, for example, it's not like a flexible as we compare in the
stochastic games. I mean, I didn't discuss that, but we have this worked on, and you can find my papers on that, with sensitive mean field games, where it brings in a robustness element, so which are much less sensitive to inaccuracies in the modeling of the problem.
So one more problem, one more question. So sorry. So since we have a COVID-19 situation all around the world, so actually there are some game models actually designing for modeling, modeling some problems in an epidemic environment. So it could be two-player games, multiple player games. So here, for example, I also want to consider one model. I actually want to design one model, but I have some precautions, some queries about this subject. So, for example, I design a model like, for example, we have a model like SIR model. So it's like epidemic model. Let's consider one model. So we have one model, and we can consider actually two models out of one. One for a pursuer and the other one for the invader. So we can actually the problem is actually those two problems built in discrete environments actually. So the question is this one. So whether it is possible to the pursuer build a strategy to catch the invader within, again, a small environment, within a small range. So actually those players, moving one period at a time. For example, if invader is moving one shot, let's say taking one shot, the pursuer also following one shot, but the position is not, actually the position could be the number of patients or the number of other things, medicine, some kind of these things. So is it possible to model environments like that? Actually, this is my question. I built one, but I have some suspicions about this, because we have done because to design for these problems, it becomes weak if we don't have any equilibrium. All right. So we need to mention about some equilibria, for example, Nash equilibria or some other equilibria for those problems. So that's why I just a comment is necessary for.
Well, there is we have done quite a bit of work on epidemic models, and most of it is for control purposes. How do you control the epidemics? We have. I can send you some of those papers. But then and we also had, before even the COVID time, we looked into the some game aspect of epidemics, And how can you, for example, you have to look at it as a network, and of course, if there are two nodes are connected with an edge, then those one node could infect the other one.
Yeah.
If there's a high probability of infection, then you eliminate that edge. So what that essentially means that you are having a lockdown for one of the nodes. So therefore, there won't be any mobility from one node to the other. So you can formulate these as game problems.
Yeah.
And so that's one answer, and I can send you some papers. And the other one is from that discretization problem that you formulated, where it is like the pursuer does not know where the evader is, the evader doesn't know where the pursuer is, or they can only know each other if they are within their visibility range.
Yeah.
So there are pursuit evasion problems where you can have visibility constraints. Only if they come within a certain radius of each other, then they can observe each other, then the nature of the solution, the strategy changes, because now it's a function of the location of the other player. There's a rabbit and hunter, famous rabbit and hunter game that people have looked at, and I have also looked at that. And I can send you many years ago, I can send you that paper as well, where the hunters, so they move one cell at a time. And the rabbit also jumps. Rabbit also jumps, and the hunter wants to shoot the rabbit, but it can only shoot the rabbit if it's within a certain radius.
Of
the rabbit. And so the question is, what are the strategies of the hunter in that case?
Beautiful, Professor. Yeah. Thank you. Those are all my questions, but we have three more questions, Professor. Okay. Sorry about that.
Yeah.
If you have time.
I have about at most 10 more minutes because I have
okay. I will be fast. I will be fast. So the one question as follows: how does physics affect game theory? Is there a big jump between 2D and 3D environment? The question is something like that.
Well, the physics definitely. I mean, the thermodynamics and physics and the atoms are movements, and the motivation that we develop from the approach of physicists to such problems, that is, you go by the aggregate and you don't look into individual dynamics of the atoms, for example, that has a strong connection to mean field games. And people have used, especially in the PDE, partial differential equation framework, models of that type, motivated by physics. And in game theory, of course, the kinematics also play a role, because if you have aircraft, then you have to take into account the dynamics of an aircraft, and if you are just controlling it, like in a pursuit evasion game, aerial combat games, then you cannot move the aircraft in any direction, because there are holonomic constraints. And so therefore the kinematics and therefore the physics come into play there. But the game theoretic models go beyond physics, and because you can deal with much higher dimensional systems, not only 3-dimensional systems. But the other thing is, much more recently, the quantum computing has been definitely is an emerging area, and the quantum physics has a lot to do with it. And now there is, I mean, this is still very preliminary, research, but the game theory also comes into picture in designing secure quantum computing systems. And now the hope is in the future is that through quantum computing, you'll be able to do things at maybe even solve NP-complete problems, and so fast. But then there is if you are using quantum computing in transmitting messages, then there are security issues, and game theory comes into play, and there is this entanglement, which is an important concept in quantum theory, and which arises in quantum computing, which essentially brings in correlation between different actions, and correlated equilibria does the same thing. So, but this is a very unexplored area, and I'm sure the next 5 years or so will show us the directions in which this would be moving.
Thank you, Professor, for your answer. So the second question is the following. Are there any game theories which using in real company life that haven't got evolution in system? Can you give an example?
So in what? In companies, by companies?
Yeah, real company life.
Well, the game theory is being used by companies in determining their prices, mm-hmm. and of products, because they have to take into account what the reaction, when a company determines at what price to sell an item, to market an item, they have to take into account, let's say that they want to maximize the profit, but it's a network system, and there are different participants. Of course, there is the consumer. The question is, will the consumer like it at the price that is offered or not? And the other thing is, if there are other companies that is producing a similar, maybe not the same quality, but a similar type of product, then how are they going to price them? And so this is like a Stackelberg game. And how do I take into account that possibility and online make adjustment on the prices and the level of production and so on. So it is for planning purposes and for pricing purposes, this game theory plays an important role there. And this also shows utility companies in pricing electricity and electricity pricing and having different prices for different times of the day, so that you take the individual's responses into account, and essentially for electric companies, for power companies, the main thing, one of the objectives is to have uniform usage of electricity to the extent possible. That is not to avoid peaks. And the question is, can you adjust prices in such a way that it will give individuals incentives to do, for example, laundry or dishwashers and so on at times where the price is low and when the usage is not as high. And so there are many applications of game theory in situations where you have to involve different participants, both as competitors as well as price takers.
So actually, Professor, here we have a non-cooperative games, right? So we have a
non-cooperative game. Now, of course, there could be government regulations which will prevent the companies to do pricing fixing. And
taxing, or
if there is pricing fixing, then that becomes a cooperative game as far as some of the companies go, and this would be a coalitional games come into play. But generally, in most democratic countries, there are regulations which prevent the companies to be dominant in the in the market, and to avoid price fixing the prices.
Thank you, Professor, for your answer. So the last question is the following. I saw a name, John Maynard Smith, in the beginning.
Right.
So can a biologist use game theory in that field today? Can you give me an example? I'm asking this question as a medical student. So this student, medical student.
Well, this is, yes, this I gave the reference, the name of Maynard Smith, as because he was one of the recipients of the Crawford Prize, and it was on evolutionary games, and definitely some people view as viruses as going against the human internal sort of a system, and you can view this as a game, how the viruses evolve in the body, and how it would different individuals would infect each other, and so there you have multiple individuals as well as the within the body of an individual. You can view it as virus being an adversary and trying to do things which you want to avoid. And
yes.
And so the evolutionary games is of course on a much slower scale. The evolution takes place, but there is enough evidence that game theory is in other words, the species try to survive. They go for survival, but then there are others who want them not to survive, other types of species. So there is a constant sort of a conflict of interest in the nature.
Mm-hmm.
And who wins, who doesn't win, and this is all probabilistic, and that's what Maynard Smith has looked at. And there's a whole sort of the handbook that I have referenced. It has chapters on evolutionary game theory, and there are many applications there. As far as the medical profession goes, the testing is an important thing where game theory plays a role. If you cannot test everyone at the same time to see whether they are positive or not, how can you take a sample, proper sample? How do you choose a sample in order to test individuals? And what are the statistical properties of that sample? After you test, based on the outcome, how do you pick the next sample? And so those are also problems that game theorists are addressing, the testing, and the same thing is in the, I mean, we have papers where we do testing by companies as to see whether their product will be viable and will be accepted by the community.
So actually, Professor, there are many problems actually, as you said. One, you discussed, so finding a suitable spot in the Swanlund. So it's like near field games. So we can actually, I'm just saying, you know, it could be actually designing it's possible to design one model that not approaching to sick people. So we can see those spots, for example, crowds as a sick people. So we want to prevent the disease, like a social distance, putting some social distance, those sort of things. So actually, mean field games also motivating. I see here. So the last question, actually, that question came in 2 minutes, actually. So this is the last question, Professor. So
sure.
How can we use the dynamic game theory in blockchains? I know the person who asked this question.
In what?
So,
in
blockchains.
In blockchain models.
Yes.
Well, I'm not an expert on blockchains, but I do see. I mean, that's a very sort of an emerging again area, especially in some of my communication faculty are working on, where anywhere where you have, I mean, it's again a situation where you have multiple decision makers, multiple people involving, and there's a large high population there also. So I would think that the mean field games would have a real application there. I haven't seen yet as any serious work in that direction, but I would think that given that it is like a stock market where you have again many individuals and a single individual cannot make any major impact. So that's again a mean field sort of a scenario. So I would think that the blockchains would be the future of that, would have some game elements embedded into it. But I'm not an expert on that, so I cannot say.
Thank you, Professor. Thank you for your time.
Sure.
It's really honor for me to moderate this beautiful talk. And I will continue in Turkish. Hocam çok teşekkür ederim. Çok sağ olun zamanınızdan dolayı. Gerçekten müthiş. Yani sizi de yorduk hocam. Çok
rica ederim. Memnun oldum. Başarılar, çalışmalarınızda başarılar. Yine herhangi bir sorunuz olursa çekinmeden yazabilirsiniz.